force on current carrying straight wire. In the diagram, there is a current carrying wires inside a region of magnetic field strength B. In the presence of uniform magnetic field, the current carrying straight wire will experience a magnetic force of magnitude F equal to ILB sine theta, where I is the current, B is the magnetic field strength, L is the length of the wire covered by the magnetic field, and theta is the angle between current I and magnetic field lines B. The direction of the magnetic force, or we say the motion of the wire, is determined by Fleming's left-hand rules, or we say the left-hand rules. Using the left hand, the thumb represents the direction of the force, and the first fingers represent the directions of the magnetic field, and the second finger represents the direction of current I. Notice that F, B, I are mutually perpendicular to each other. This is an example of the respective directions of I, B, and F. You can check it by using the left-hand rules. Notice that if current I is perpendicular to magnetic field lines I perpendicular to B, then the magnetic force on the wire will be equal to ILB since sine theta equal to 1. However, when current I and magnetic field are parallel, theta equal to 0 degree, therefore the magnetic force on the wire will become 0 since sine 0 degree equal to 0. Let's use left-hand rules to find the direction of the magnetic force in each of the following cases. In case A, the magnetic force on the wire will be towards the left. In case B, since only the direction of current is reversed, the magnetic force direction will also be reversed. That is, the force is towards the right. In case C, the direction of the magnetic force will be perpendicular to the wire and is in this direction. In case D, the magnetic field lines produced by using a slab magnet is towards the right and is uniform. By using left-hand rules, the directions of the magnetic force on the wire will be downward. In case E, the magnetic field lines are downward. By using left-hand rules, the magnetic force on the wire will be into the plane of the paper. For case F, since the direction of current in the wire I is parallel to the direction of magnetic field, therefore there is no magnetic force acting on the wire, F equal to 0. An example, a wire suspended vertically between the poles of a magnet as shown in the diagram. When there is no current in the wire, it remains vertical. Explain what happens to the wire when the current is A, upward, and B, downward. In case A, if current is upward, By using left-hand rules, there is a magnetic force acting on the wire which is towards the left. Therefore, the wire will bend towards the left as shown. For case B, if the current is now downward, by using left-hand rule, the direction of magnetic force acting on the wire will be to the right. Hence, the wire will bend towards the right. Turning effect of a current carrying coil in magnetic field. Consider a rectangular coil is put inside a region of uniform magnetic field produced by two slab-shaped magnets. In the side view, assume the current flows in the direction as shown, and the magnetic field lines is directed from the north pole to the south pole as shown in the diagram. By using left-hand rules, the direction of the magnetic force acting on PQ will be downward, while the magnetic force acting on the wire XY will be upward. Hence, there will be a moment acting on the axis of the coils due to the force. In this case, the coil will rotate anti-clockwise. Now let's consider the front wheel. From the front wheel, we see that along PX, the current at P is into the plane of the paper, and the current at X is out of the paper. Since magnetic field is towards the right, by using left-hand rules, we have the magnetic force acting at P will be downward, and the magnetic force acting at X will be upward. And the couple, or we say the turning moment, produced by this pair of force will be equal to F times D, where D is the separation between this force. And because F equal to ILB, therefore the moment acting on the coil is equal to ILB times D, equal to IBA, where A is the area of the coil. To increase the turning moment, we can use more turns of the coil. That means we can increase the number of turns. If there are n turns in the coil, the total moment will be NIBA. How a DC motor works. A DC motor consists of a DC supply, a permanent magnet, a rectangular coil, a pair of commutators, and a pair of carbon brushes. The carbon brush is used to fix the commutators so that the coil will not rotate away from the axis, and the commutator will rotate with the coil. In stage 1, when the plane of the coil is parallel to the magnetic field, by using left-hand rule, the magnetic force on XY is upward, while that on PQ is downward. Therefore, the coil will rotate clockwise. At stage 2, the plane of the coil is perpendicular to magnetic field. Since the commutator now loses contact with the brushes, therefore there is no current. So there will be no magnetic force acting on the coil. However, due to inertia, the coil still rotates clockwise. In case 3, the plane of the coil is again parallel to the magnetic field. However, the position of XY and position of PQs are interchanged as compared with case 1. In this case, the current in XY is reversed compared with the case in 1. Therefore, the magnetic force on XY is now downward. However, the magnetic force on PQ will become upward. In this case, the coil still rotates clockwise. In case 4, the plane of the coil is again perpendicular to the magnetic field lines. Hence, the commutator is again losing contact with the brushes. Therefore, there is no current in the coil. However, due to inertia again, the coil will still rotate in a clockwise direction. Notice that the commutator is very important for a DC motor because it reverses the direction of currents along XY and PQ for each half revolution, from stage 2 to 4 and from stage 4 to 2 again. So the force on XY and PQ reverse direction too. As a result, the direction of rotation of the coil remains unchanged. An application of magnetic force is loudspeaker. A loudspeaker consists of a C-shaped permanent magnet and a coil of N turns wound on a paper cone, with the paper cones movable inside the C-shaped magnet. When the current flows through the coil as shown, when we see the cross-section of the diagram, for the upper part of the wire, the currents are into the plane of the paper, and for the lower part of the wires, the currents are out of the plane of the paper, and the magnetic fields are direct from the North Pole to the South Pole, that is pointing downwards. By using left-hand rules, the magnetic force acting on the wires in the upper part will be inwards. Also, the magnetic force acting on the lower part of the wire will also be pointing inwards. Therefore, the paper cone will move to the left. For a loudspeaker, the current is alternating current. When the current direction is reversed, the magnetic force acting on the wires will be towards the right. Hence, the paper cone will move to the right. If the input alternating current is of frequency f, the paper cone will oscillate to and fro with a frequency of f to reproduce the sound wave of frequency f, which is the same as the frequency of the input AC. louder sound can be produced by increase the current, or using stronger magnet, or using more turns of coil.